I want to review a few of the topics that were covered in the text, but questions that arose during class discussion. Here's kind of a short list of the items that are going to be covered in here. First is our waves and our types, what's different between a transverse and a longitudinal waves. Waves and their reflections, as we have waves that travels, what happens when they end up coming to an end, either a fixed end or an open end, and the reflection that's caused from that. The idea of superposition, or when waves add constructively when they get larger, or destructively when the resulting wave is less in amplitude than either of the applied waves. And then when we have waves moving in opposite directions, the constructive and destructive interference that we end up seeing there. Okay. First, we'll take a look at a couple of pulses. It's easier to see what's happening for the interference there, and then we'll take a look at the waves, those continuous motions, and then we'll see how this adds up to standing waves. And let's get this going. All right. Pause. Here we have an example of a wave on a string, or a transverse wave. Notice the medium is moving up and down. Remember, the medium is the material that the wave is traveling through, but the wave itself is moving from left to right. Kind of follow that along. Kind of a wave moving there. The medium is moving perpendicular to the direction that the wave is propagating through the material. I like to think of it as making kind of the letter T. And this would be on its side, that our medium is moving up and down, but the wave itself is moving from left to right. Here we have an example of a longitudinal wave. A sound wave is a popular example of a longitudinal wave, or if I gave a slinky a shove rather than a wiggle side to side. This one is a little bit hard to see, but you can see there's kind of a wave passing through this, and within the material, these are supposed to be, let's say, air molecules. They only move back and forth, but left to right just a little bit. You see the wave is moving from left to right, but each of these particles are moving left to right. I'm going to increase the frequency and increase the amplitude, just make it a little bit easier to see. Now you can start seeing the wave passing through from left to right a little more easily. But if we follow the motion of any one particular dot, I'll pick this one here, it moves a little bit to the left, to the right, and back to the left, and back to the right. Right, let's increase the amplitude of this to make it even more obvious. Now I think you can see that we have a wave that's passing through the material from left to right, but if we follow any one, we'll call it an air molecule, it moves to the left, moves to the right, moves back to the left, moves back to the right. So that the direction of the movement of the medium, in this case left to right, is the same as the movement of the wave through the material from left to right. That is a longitudinal wave. Remember that a wave is an oscillation that travels from one place to another, and to isolate that more easily, we can give a single pulse and watch how that goes. Okay, so I'm giving a pulse. We can see that is moving from left to right. We can see that it's starting at this oscillator and continues on. This would be the example if we had an infinitely long rope, or we're sending radio signals from a radio station. They just keep on moving out. Let me give another example of that. Okay. If we put a collection of pulses together, then we have a wave. But it's easier to see this if we just look at a single pulse. Okay. Hey, but what if it doesn't go on forever? We have some type of a different end. And for example, let's say we have a fixed end. We're going to clamp this end of the wave and give it a pulse. Okay. Watch what ends up happening. As the wave is going along, it's picking up the next part of the medium, picks up the next part of the medium. But if we get to a position here where the medium ends up being effectively very heavy, it can't pick it up, and the medium pulls the wave back down. Okay, we can see we get a reflection back on the opposite side of the rope. If we have an upward pulse going one direction, it's a downward pulse going back the other direction. So that's when we have a fixed end. Waves and pulses carry energy, and energy is conserved. And if I can't have it continue on, something has to happen. And so it's contained within our two boundaries. It just keeps bouncing back and forth. The energy is not lost. It's conserved, but it just ends up bouncing back and forth between the two ends. Let's go ahead and reset this one. Okay, we're going to go to a different type of an end. Instead of it being fixed, we're going to have a loose end. This one, when a wave gets down to this end, we can just see there's a ring to guide it along this pole, but there's no weight to it. We know a wave moves because it's applying a force to the next part of the medium, lifting it up or pulling it back down. If I get to the end and there's nothing to lift up, we'll find out what ends up happening. I've given the analogy that it's like, let's say if you tried picking up a series of weights and suddenly you have one that weighs a lot less and you didn't anticipate it, you would end up lifting it quite a bit higher. Okay, let's see what happens here. We'll give this a single pulse. All right, so I'm going to give a single pulse, traveling down to the end, lifting up each part of the medium. When it gets to the pole, it lifts up quite a bit higher and we get a reflection. Notice in this case, instead of being on the opposite side, it's on the same side of the string. Okay. When it gets to the fixed end, then it ends up switching side because that can't be moved. This end, it actually moves so much it pulls the wave back in the same direction that it arrives. So as we see it move from left to right, it's pulling up each of the beads. When there's no bead, it lifts it up quite a bit higher, okay, and then sends a wave back on the same side of the string. It gets to a fixed end, it flips over. Okay. Why doesn't it just continue on? Hey, there's no medium out here. We need to conserve our energy, so it ends up, just like we had last time, just bouncing back and forth between the two sides. When two waves arrive at the same place, the resulting wave can either be larger or smaller than the two waves arriving. In this first example, this would be similar to a wave coming from one speaker in the room and a wave coming from the other speaker in the room. Hey, if the peaks from each of the speakers arrive at us at the same time, or the valleys, the troughs as they're referred to, arrive at the same time, then we end up getting an amplitude that's much larger than the two waves that arrive at us. That's known as constructive interference, when the amplitude of a resulting wave is larger than the amplitude of either of the incident waves. The other type of interference is destructive, and you can see that here, where the crest of one wave arrives when the trough of another wave arrives. The resulting wave has a much smaller amplitude. This would be similar to as we walked around the room hearing two speakers at the same time, where it was very quiet. We ended up having areas of destructive interference. So constructive is where it's much larger. Destructive is where it's much quieter. This can happen as waves pass through each other as well. We have an example of a pulse moving from left to right. So you can see in sequential pictures, this larger pulse is going from left to right. Okay. And then we have this smaller bump or pulse that's going from right to left. Each of these are, let's say this is at time 0, time 1, time 2, time 3, time 4. The dark line here is the sum of the two waves. And we can go through point by point and add these up. We can see at this point they start overlapping. We end up having a larger amplitude here, a non-zero amplitude, instead of that zero amplitude that's here. When they completely overlap, we can see that there's constructive interference, that the sum of the amplitudes adds to a larger wave that is larger than either of the two waves. As they pass through, a small bit of interference, and as they separate, there's no wave for them to interfere with, so the resulting wave is just their individual sums. Perhaps an easier way of seeing this is with square waves. This is similar to the practice test where we have, hey, this square pulse traveling from left to right. We have this blue pulse traveling from right to left, and this purple graph shows the sum of the two pulses. Okay, I'll let this thing go, and you can see as the two pass through each other. Right, play. I'll go ahead and I'll reset that, and I'll pause it as they're approaching each other and start overlapping. Okay. Hey, so we can see that right at 4 seconds, the only pulse that's present is the red pulse. So that's one box up, an amplitude of 20 millimeters. So we see that our resulting wave is only at 20 millimeters. At around 4.5, between 4.5 and 4 3/4, both pulses are present. So we have the red pulse is at an amplitude of 20 millimeters, the blue is at plus 20 millimeters, the resulting pulse where they overlap is at 40 millimeters. After we get at about 5 seconds and beyond, there's no more red pulse. We said it's only the blue pulse at 20 millimeters, and we see the resulting wave is at 20 millimeters until we get to the end of the blue pulse, and it drops back down to 0. We'll step through this. Okay. Just moving it a little bit forward. Okay. Hey, at this point, our resulting wave, we have a maximum overlap between the red pulse and the blue pulse. And so for the entire length of the red pulse, the resulting purple pulse is 40 millimeters in amplitude. Let it go all the way through these. Each of these simulations is available on the Schoology page for today. We can change the shape of that pulse. We'll have two triangles pass through each other. Those are examples of constructive interference. They add, okay? Or we could end up changing it so one is up and one is down. This, as they overlap, would be examples of destructive interference. The amplitude of the resulting wave, or the sum, is going to be less than the amplitude of either of the waves that are heading toward each other. Hey, so our waves usually are not these easy to deal with squares or triangles, but have that more characteristic sine wave pattern. And here we have a wave traveling from left to right and a wave traveling from right to left. Okay, they overlap. They're both, let's see, positive amplitudes. So we see when they overlap that we get constructive interference. Here we have one pulse positive, the other pulse negative. Notice as they pass through, we get destructive interference. I'm just going to see if I can stop it just as they're fully, let's see, interacting. So you can get something that is close to there. Okay. I almost caught it. This has almost 0 amplitude here, even though we have two pulses that are passing through each other. And continue that. Hey, this becomes important when we're looking at standing waves, because this wave traveling from the right and wave traveling from the left, instead of being from different sources, can just be reflections. Okay. That becomes the basis of our standing wave. Hey, here we have a wave traveling from left to right, the red wave. We have a wave traveling from right to left, our blue wave. They're traveling on the same string, okay, and then we're looking at the two waves added together. This will look a little bit like our recent lab. Notice, okay, at this point we have an area where it's not moving, so we know that's a node. Okay, but why does it not move at all? Let's take a look at our two waves. Okay, remember with waves we can end up adding them together. Notice every time our positive wave, let's see, I'll play that again, reset. Okay. Our red wave is positive, our blue wave is negative by the same amount. When they're both at 0, they're at 0. When our red wave is negative, our blue wave is positive. They're always, let's see, exactly, let's see, a fancy word, out of phase. One way of saying is this is as much up as this is as much down. So they actually add to 0. And that happens on this right end as well. Okay, whenever the red wave has a positive displacement, the blue wave has a negative displacement. Let's take a look in the center. Okay, when red wave is up, blue wave is up, we get a large positive displacement. When red wave is down, blue wave is down, we get a large negative displacement. This only happens at certain wavelengths and certain frequencies. You found that in the lab, in our homework, that this occurs at a fundamental frequency, harmonic equal to 1, or its multiples. In your lab, you saw something that looked like this. At a harmonic of 2, that means we have 2 bumps. Okay, but how many nodes do we have? 1, 2, 3 nodes. Okay, so we know that at the end that as much as red is up, blue is down. But let's take a look at what's happening in the center. Okay, in the center also, when blue wave is down, red wave is up. When red wave is up, blue wave is down. When one wave is 0, the other wave is also 0, so they add to 0. Okay. You do it with 3 or 4. Notice the speed of the wave in each of these is staying the same. Its wavelength and frequency are changing. So for a standing wave, keep in mind that this happens at certain frequencies, certain wavelengths, because we have to have our nodes and antinodes at very specific locations and multiples of our fundamental frequency.